This scenario is an illustration on how we can cascade different reference motions. We've seen examples where we've done hill pointing or maybe velocity pointing or location pointing, and that was one reference frame. But let's say you want to be hill pointing, and then relative to it, you might want to be doing a rotation. So keep your one axis pointing radial outward, but have the other frames actually rotate around that. Or maybe you want to rotate and twist relative to the hill frame. Often this is done in one-off modules with all the complicated kinematics baked in, but Basilisk contains dynamic reference modules which don't specify a particular absolute frame like hill pointing, but rather it says just rotate about your one axis, or rotate about your two, or rotate about the 3 and 2 axis in that sequence. And you could do MRP rotations or Euler angle rotations. So you can specify it using either Euler angles or modified Rodriguez parameters. The scenario inertial spiral is a demonstration of this. And here we will have Euler rotation, which prescribe a 3-2-1 sequence. So if you have to do a 3 rotation, then a 2, you can do it in one module. But if you have to do a 2 rotation, then a 3 rotation, you'd have to use this module twice. Then doing purely 2, then cascading it to a 1 rotation or a 3 rotation. Depends on your sequence again. So anyway, that's the demonstration, and we'll run it, and you will see that we actually track asymptotically that dynamically created reference motion, which is pretty cool, actually. So what does the script look like? Single process, single task. We're running for 10 minutes. We're taking 10 Hertz. We're doing full attitude control here, so we're doing small time steps. Create the spacecraft, create Earth, create the external force torque, create simple nav, pretty much standard modules you've seen with all the other attitude simulation ones. Then we're doing inertial 3D, setting the reference to the origin, just because. You could have also made this a standalone message, quite frankly, if it's just a static thing. But here we have a module creating that particular inertial pointing reference. Now, we don't just want to line up with 0, 0, 0, but relative to the inertial frame, we would like to do the following sequence. And this sequence was done in particularly so where we have to make 2 modules. So we're asking for a 1. So if this is your 1 axis, your 2, and your 3, we want to rotate about our 1 axis and first, and then we want to do superimpose the rotation about the 2. And this will actually give a spiraling motion of the 1 axis. And we'll illustrate that when that runs. So we use Euler rotation, make an Euler rotation modules. These are always 3-to-1s. And if you just need a 1 rotation, then you just specify a non-zero rate about the 3rd axis, and that's it. So again, if you want more information, you can always take the module name, go to the documentation, and actually I've already got a link here. You can go in there and then see about the user guide. And you can specify initial angle set. If you don't, they're just going to be 0. In this case, we're just using 0, but the Euler angle rates are particularly the ones you have to specify. So that's what we're doing here. So this will rotate about, again, 3, 2, 1. So the last one is the 1 rotation, not the 3 rotation. That's 1 rotation. Now we want to do a 2 rotation. So now we do another Euler rotation module, and you will see while the first Euler angle rotation attitude ref in message subscribed to inertial 3D output message, the second Euler rotation angle subscribes to the first Euler rotation angle output message. So these can be cascaded together to your heart's delight. And we're specifying 0.0001 radians per second as the rotation rate. Again, here still with 0 initial angles, everything starts from the origin. The rest of it is pretty straightforward. We do our attitude tracking error to get our guidance message. That guidance goes into the MRP feedback, and then that connects again over to the external force torque object. So all of that looks similar. The only thing different is we're not connecting the output message of inertial 3D, but the output message of the second Euler angle rotation sequence module. And that gave us the final guidance. So we have a static guidance plus dynamic guidances as a references, all superimposed, and the math internally is fully resolved. So you're not dropping anything. You will get sigma Rn, omega Rn, and omega Rn dot. And then we set up recorders, run the sim, everything is pretty much standard. So let's see what this looks like. If I run this scenario, It takes a second, but you can see that one axis, how it starts to do this spiraling motion, because we're twisting about the one, that was the one rotation sequence, and then we're also actually rotating about the two, which will make it pitch outward, and you end up with this ever increasing spiral. So if you had to do a spiraling motion around the target, searching for something, or just scanning out a planet area, you could do all of that without writing a single line of C code, just using existing modules. The Euler angles, I'm just plotting them what they look as they start to grow and grow. The tracking error rates converge to 0, as you'd hope, as do your control torques, and of course, importantly, your attitude tracking errors. Even though we weren't tracking this reference to begin with, it asymptotically starts to track and gets there. So this was an illustration of how to do attitude guidance and how we, attitude reference generation with a static initial frame. Here we used inertial 3D. But we could have also used, hill pointing. You could have done this on top of hill pointing. If you always want to look down on the planet and start scanning spirals and then reset it, maybe go backwards, you could do that and keep continuously spiraling on top of a hill, circular orbit, elliptic orbit, hyperbolic flyby. It's really just limited by our imagination. So go have fun with attitude references.